And the topic is scalar conservation laws. First of all, each lecture will start with a brief reminder of the most important things from the previous lecture. So the most important thing was system of set of Euler equations. So we discussed the importance of CFD as it is. Why do we need? So what does it mean? Computational fluid dynamics. What is the difference between fluid and gas and solid? And why do we need CFD? That's not an actually easy question. And what is the relationship between simulations and full-scale experiments? And the second part of the first lecture was about the Euler equations, because, as I told, everything within the scope of this course will be about the solution of equations that describe the motion of inviscid media, compressible media, that is gas. And we considered the integral conservation laws and discussed some issues, namely that we also should add entropy inequality to the defining system of equations, and so on. So what you must know, so the first equation in the set of Euler equation is mass conservation law. d rho over dt plus d rho u over dx equals to 0. The second one is momentum conservation law. So actually Euler derived this equation, and in books sometimes this equation is called is referred to as Euler equation, not the whole system, but this equation, momentum conservation law. Here we have the pressure. We should take into account the work of pressure forces. So the third equation is energy conservation law. Here we have E, total energy. So total energy consists of kinetic term and internal energy of media. And we should somehow close this system of equation and define the property of our media. So the simplest possible equation of state is equation of state for the ideal gas. So, and here we should know the thermodynamics of our media. That is why, so if you simulate the motion of compressible media, we should take into account the energy equation, and we should know the thermodynamical properties of our media, specifically this gamma specific heat ratio, for example. So here, within the scope of our course, so gamma will be a constant. So no, we will not consider difficult equation of states and difficult media and so on. We discussed that that's not enough. So formally, that's enough. We have density, velocity, pressure, so 3 unknowns. And if we put this E and this epsilon to the energy conservation law, we will have 3 equations for 3 unknowns. But then that's not enough, because we also should add entropy inequality or take into account the second law of thermodynamics. Otherwise, we can get wrong solutions. And today we also see it on the example of scalar conservation law. So sometimes numerical methods, they do not take into account entropy inequality, and in this case they can provide you with wrong numerical solutions. That's very important. Usually in papers, this entropy inequality is not written, but it is mentioned that it should be valid. So here rho is function of x and t, it's density, u is velocity, or more accurately is the projection of vector quantity velocity onto chosen coordinate direction. And p is pressure, and E is total energy per unit of mass, and epsilon is internal energy per unit of mass, and S is specific entropy. So you should know this system of equation, because many times we will refer to it, and so you can just remind it, and you know, when you meet it, you should understand what does it mean. That was the most important outcome of our previous lecture. And this was an example. What does it mean? So why do we need you know, this entropy inequality, and what are the difficulties with these Euler equations? The problem that is that sometimes even with entropy inequality, these equations admit several stationary, as a rule, it's valid for stationary solutions. So the solution of the system of equations may be not unique. So you have, it's possible to have several solutions. For example, this is one of the most important or known example, is the interaction of a stationary supersonic flow with a wedge. So suppose we have a supersonic flow, it interacts with this wedge, and it is known both from theory and the same is in full-scale experiments, that the solution is not unique. So this, if the theta is less than certain value, you will have attached shock wave, and two possible positions for this shock wave is possible. So so-called weak solution and strong solution. So the question is, we will continue with this example. The question is why in some situations you will get weak solution, one strong solution, and in reality and in simulations, how how can we, you know, make a distinction between them, and so on. So the most important things here, that even take into account the second law of thermodynamics, Euler's equations may not have a unique solution. So this is the first point. So the second point, as a rule, it is valid for stationary flows in the presence of discontinuities. So usually this happens when you have solutions in the form of discontinuities, shock waves. And that is typical for compressible media. So once again, we discussed previously the differences between compressible media, incompressible media. So these shock waves are for compressible media when the changes of density are significant. A well-known example is interaction of a stationary supersonic flow with a wedge. So weak and strong solutions are possible. Okay, let's continue with this example, the problem of uniqueness of solution. So on previous lecture, I recommended you several books, and I also sent it to you in our WeChat group. They're in English, so books of Toro, Levecchio, and so on. But I also will use some, books in Russian for sure with the translation, because in Russia there are a lot of good books on this topic. For example, this book called Gas Dynamics from Cherny. He's one of the most famous gas dynamics researcher in Soviet Union. So the first point, so it's just not mathematically strict statements, but some results that are generalization of experience of people who computed the steady flows around bodies. So when considering only the steady motion of an ideal gas, it's not possible in the presence of multiple solutions to formulate a general criterion for selecting a unique solution. So when several solutions are possible, generally speaking, you are not able to choose one or another. So depending on different conditions, you can get one and you can get another solution. So the solution, so the first idea, maybe we should take into account the stability of the solution. So from mathematics that, for example, you can get different stationary solutions, but some of them can be stable solutions and some of them can be unstable. For example, this classical example when this ball on the surface. So this situation and this situation, they are both stationary solutions. So if you put ball here and here and do not touch them, so they will keep their location. But if you give some small disturbance, so this ball will fall down, and this will be, so it will oscillate and keep his location inside this cavity. So maybe the solution of the problem of steady flow may be unstable with respect to certain flow disturbances. And this may serve as one of the criteria for selecting among possible solutions. So we should take into account the stability of the solution. That is why, one of very well-developed area in this field is the analysis of stability of solutions of Euler equations. That is why people know how to linearize the solution around the stationary points and so on. And this field is very theoretically developed. Another idea, so how can we get the stationary solution? So we can start with some transient process and wait. And so if the configuration of the problem is so that you expect to get the stationary solution, you will get it after some period of time. So if the solution of the steady flow around the body is obtained as the limit of the unsteady problem solution at t goes to infinity, which forms the basis of certain numerical methods. So in experiments we can do that, and in simulations. So in simulations we can solve stationary problems using our transient solvers, just waiting for a long time. The so-called time Martian method. So in simulations you can also solve stationary problems using non-stationary solvers. Then flow regimes that are unstable with respect to disturbances may be automatically excluded. So maybe if we try to get the stationary solution through the non-stationary simulation, some disturbances will disappear, so they will be excluded by our numerical method. On the other hand, there may be cases in which, although a unique solution to the steady flow problem exists, it is unstable. So even though if you have one stationary solution, in reality periodic oscillatory flow regime may occur. So for example, you consider the flow around just a cylinder, and you can expect some stationary picture flow field. But in reality, the flow will pulsate and oscillate around the body. That's also possible. So finally, it has been suggested that considering the solution of the steady flow problem around the body as a limit of unsteady solutions within the class of piecewise continuous functions ensures obtaining the required unique solution. So once again, people thought that maybe we should get the stationary solution as a result of some limiting process for non-stationary solutions. But from a mathematical point of view, it was not proved. So this is some historical page. Gremir Cherny, so the author of his book. So he was a Soviet and Russian mechanics scientist, and he was engaged in a wide range of gas dynamic problems and high-speed aerodynamics. And actually, he was a veteran of the Second World War, so it was typical for that time. And so his scientific interests included hydromechanics, theoretical and applied aerodynamics, gas dynamics, combustion and explosion. So he contributed to the field of. So once again, so at the beginning of this science, it was very typical that people were experts in many fields, compressible, incompressible, also fundamental issues and aircraft engines. So practical and fundamental issues. He is known for the results on shock-wave boundary layer interactions, so we do not consider these specific problems of aerodynamics, but so they're very complex and demand both, at that time they did not have opportunity to use supercomputers. That is why they were very clever, and they provided and built analytical solutions for all these problems. They're still important because when you get some numerical result, first of all, so you try to understand if it's correct or not. And in this case, you need these books to estimate the correctness and the relevance of your results in comparison with the known exact solutions for these problems. Also, the problems connected with the study of atmospheric entry of bodies at space velocities, so all these space problems and so on. So the first idea that maybe we should take into account the stability of our stationary solutions, and and maybe it can help us to find one or another stationary solution if several of them are possible. Also, another idea is that in reality the media is not inviscid, it's viscous, and maybe we can. It has also been suggested that the uniqueness of the generalized solution to the steady flow around the body can be ensured if the solution is considered as the limit of continuous solution of the same problem with the viscous gas model, as the viscosity coefficient approaches 0. I will show now the Navier-Stokes equations, and the idea is that if we decrease the viscosity coefficient, then Navier-Stokes equations goes to Euler equation, and maybe if we consider this limit for viscous solutions, maybe on this way we can get some unique, the most correct solution for Euler equations that I call generalized solution. So in Soviet and Russian books they call generalized solution. In English usually they're called weak solutions. So they're the same. In general, however, steady solutions should be regarded as the limit of unsteady solutions. So another idea that maybe we should solve Navier-Stokes equations, and in the limit of vanishing viscosity we can get correct solution of Euler equations. And on this way we approach into the topic of this lecture. So Euler equations or Navier-Stokes equations, they are very, very difficult for analysis, for numerical solution. That is why people try to consider so-called simplified models, or toy models even they're called. So I don't like this term because it's not too serious, but actually it's a relevant term in scientific literature. So the hypothesis that generalized solutions of the equations of ideal gas dynamics can be obtained as the limit of solutions for viscous gas has in general not been proven. So from theoretical consideration, nobody proved that for Euler or Navier-Stokes equations. At present, the greatest progress on this issue has been achieved only for a single model equation in the following form. So here we will use u for velocity when we analyze Euler equation or Navier-Stokes equations, mu for viscosity, but here is just some abstract equation. So u is just some function. It's not velocity or density or anything. d over dt plus df of u dx equals to term proportional to the second derivatives of velocity. And that's, I put this quote from Einstein: everything should be made as simple as possible, but not simpler. So it's a very relevant approach in scientific research when you try to explain some effect, not to simulate some specific device such as airplane or wing or engine or something like that. When you try to explain something, the mechanisms, why do we have one effect or another effect, the approach of simplified model is very fruitful. So it's better to investigate the simplest possible model, which anyway contains the necessary effects. And in this case, you can try to explain what affect your solution and so on. That is why these simplified models are widely used, at least in this field. But why is this equation is a simplified model for Euler equations or Navier-Stokes equations? We should discuss it. The idea is the following. So we know these Euler equations. It's called conservation form. The term conservation form usually includes inside it that this is differential conservation form. So we discussed, and we will discuss it one more time today, that we started with integral form of Euler equations because integral form is the most physically relevant. But so this form is much more compact, and it's easier to understand this one. Anyway, there is also it's a mistake. It's not integral in vector conservation form. Vector, not integral. So it's possible to use much more convenient notation form. So let's introduce vector of conservative variables, u. So we will use this straight bold u for vectors. U is vector of conservative variables. Why conservative? Because in this using these variables we can have the conservation form of Euler equations. And then we also introduce f. F is a flux vector. In this case, this component-wise notation for the Euler equations can be written in this very compact vector form. du over dt plus df from u dx equals to 0, where u and f are vectors. And that is why we can just simply say, okay, let's forget at this moment that u is a vector. The u now is just some abstract function. And on this way, we get this simplified conservation law or scalar conservation law. So the topic of this lecture is scalar conservation law, scalar conservation laws. So they are called scalar conservation laws, and they are. And I try to explain to you why do we consider them. But what about this term with mu from previous slide? I don't know how to list in opposite direction. Anyway, this is the 3D Navier-Stokes equations in Cartesian coordinates. So when we solve, speaking about Navier-Stokes equations, 1D is not very important because especially for high-speed flows, because viscosity plays a significant role in boundary layers, and so these effects are 2D or 3D. That is why, just for your general understanding, that generally speaking, we should know how to solve this system of equation. You can agree that it's a bit more difficult than just one toy model, one simplified model, so-called Berger's equation. So topologically, Navier-Stokes equations. So we have the inviscid part, inviscid fluxes, and viscous fluxes. And from numerical point of view, when you try to solve it, generally the numerical algorithm comprises two parts. So first of all, we should know how to solve inviscid subsystem, so Euler equations. That is why I've told to you that everything starts with Euler equation. So if you know how to solve the Euler equation, after that you can solve many other models. You can add chemistry to the right part. You can add multi-component flow, so many components. You can add two-phase to the second phase, and so on and so forth. But the thing is that the most mathematical difficulties, issues, you get them when you try to solve inviscid part. So all these shock waves, rarefaction waves, these non-uniqueness problems, they are here for F, G, H inviscid. For viscous flux, although they look a little bit scary, actually from numerical point of view, they are much more simpler for implementation and solution than Euler equation. Here, tau, alpha, beta components of viscous stress tensor. And macroscopic motions of compressible gas are described usually in general by Navier-Stokes equations, which can be derived from the laws of conservation. Once again, they can be derived in the same manner as Euler equations, but take into account viscous or diffusive terms. So if the viscous or diffusive terms in these equations are neglected, leaving only the terms responsible for convective transport and normal pressure forces, we arrive at the Euler equations. So if you just skip all this viscosity and Navier-Stokes equations, we get Euler equations. And in numerical solution, the main conceptual difficulties usually arise when solving these inviscid equations. For example, Riemann problem, we will discuss it. Everything, all this is for Euler equations. A method suitable for solving the Euler equations can be extended, maybe not so easy, but it can be extended to the Navier-Stokes equations. We should, so how to, okay, this one. The problem is that you cannot approximate this term in a very simple manner, trying to substitute some derivatives using some finite differences. And here you can do that, actually, using some geometrical considerations. And that's the main problem. So when you try to solve inviscid model order equations, you should take into account the nature of the solution of your system. However, when you approximate viscous terms, you can do it using some geometrical manipulations, in fact. For example, consider the second equation of the system from the previous slide. So this is the momentum equation for x components. So yes, and once again, so the example of 3D. That is why we have not just one u. We have u, v, and w. We have 3 components of our velocities, and you can see that when the dimension of your problem increases, the computational costs and so the sizes of all vectors that you should store, so they also increase, and that is why the 3-dimensional gas dynamics is a source of problems for supercomputers because of, and for example, if you need to solve this problem for the simulation of flow in engine or around flow around space craft or airplane, you should have computational grids with millions and billions of computational cells, and each cell you should store this vector for conservative variables and so on and so forth. So that is why it's very difficult for the numerical solution. But anyway, consider this second equation, for example, and if we simplify this equation, we can see that it has the term time derivative. And so I'm trying to explain to you the nature of the simplified model. And so in scalar conservation law, as analog, we take du over dt corresponding to this term, and then we have these, they're called convective terms. Convective terms are substituted by df of u over dx. And then here you can see all terms that are proportional to the second derivative of velocity, or mixed, but once again second derivative, proportional to some small parameter. Actually, here it's the viscosity coefficient. And that is why we say, okay, let it be in our analog, we have this term proportional to the second derivatives of our known function, mu d squared u over dx squared. That is why this equation is used as analog for those big Navier-Stokes equations. And once again, obviously, it's much simpler than the full system of equation. If you need to understand some properties of the solutions, or you need to check some properties of the numerical method, so this equation is very important from methodological point of view. For sure, if you need to compute the real flow in real geometry, you should solve those equations. But now at this stage, if you want to learn how to solve those difficult equations, first of all, you should understand this equation and the solutions of these equations and so on. So let's summarize the simplified models for the Euler and Navier-Stokes equations. So we have discussed. So we're considering an initial value problem for the scalar conservation law. So du over dt plus d of u dx. So the first manipulation is that we can compute the speed of propagation. So df of u over dx equals to df over du over dx. So just the derivative of complex function, right? And this df over du, in some books they're called a of u or lambda of u. So this is the speed of propagation of a signal. So this form is called conservation form, and this form is called quasi-linear form. We should have some initial condition. So at this moment, we do not consider boundaries. So we solve initial value problem. That is why we solve this equation on the whole x-axis without boundaries. So another problem that in real simulations, for sure, we have boundaries in all our problems, and in simulations we should somehow work with boundaries. We will discuss it, but now, so this lecture will be a bit theoretical. So the next will be about the basics of numerical methods, but very important that we need to understand, so if our numerical results are correct, that is why, first of all, we should understand the properties of these mathematical properties of these objects, and after that we can go we can forward to the computations for simulations. So this is a scalar conservation law written either in conservation form or in quasi-linear form. The next very important object that we will deal with is linear advection equation. So linear advection equation, we have it if we choose f of u as lambda u, where lambda is constant. So it can be either positive constant or negative constant, but constant. And this equation is called linear advection equation. So it's much more, so it's simpler than this one, but anyway, it also, we will discuss the numerical methods for the solution of this. It looks like it's a very simple object, right? But actually, many issues related to numerical methods can be explained and demonstrated for this very simple model. On the other hand, if you go back, you can understand that actually this model in many aspects mimics the behavior of real Euler system. If we choose f of u as u squared over 2, we obtain the inviscid Burgers equation, also known as Hopf equation. So this is equation. This equation is also very, important, useful, and widely used in literature because it's following development of linear advection equation, but it's nonlinear advection equation. So here, the speed of propagation of disturbances is not a constant, but it depends on the solution. And for this model, we will have our today's lecture is about this the properties of the solutions for this equation. So the properties are much more difficult in comparison with just linear advection equation. And finally, if we add to inviscid Burgers equation viscous part, we have the full Burgers equation. And so this model is analog for Navier-Stokes equations. So 1, 2, 3, and so more general form when the speed of propagation is not u but just some function of u. So these four models are, I think, the most well-known and useful as analog models for Euler or Navier-Stokes equations. We will work with this one, and so mostly with this one. And numerical methods on the lecture after the following, we will consider this scalar conservation law in the form of linear advection equation. So linear because lambda is constant. So if it's not constant, so this equation is nonlinear. Okay, so we should have a break at in 10 minutes. Let's start with the linear advection equation, because there are very important concepts, and it will be simpler to explain them to you using the simplest possible model. So consider the following initial value problem. Initial value problem or Cauchy problem, they're synonyms. So it means that we have our partial differential equation, we have initial condition, and we do not have boundaries, right? So this is initial value problem. So let's choose lambda, some constant that is greater than 0. So we should specify it. Either it will be positive or negative. The beauty of this model is that we know the exact solution. So the exact solution is psi. Psi of x is the initial solution of x minus lambda t. So here we can plot the, for example, so suppose this psi of x is the initial solution, initial solution at t equals to 0. Why is this equation called linear advection equation? Because the exact solution of this problem is this initial profile which propagates with constant velocity or speed lambda in positive direction if lambda is greater than 0, or in negative direction if lambda is less than 0. So first of all, we know this exact solution, and the second good point is that the solution of this problem has a form of propagating signal or disturbance or wave. So this term waves, it's very important for Euler equations because it admits a lot of types of solutions in form of different propagating waves. And so this is one of the examples. So why u in this form is the exact solution? It's very simply to check. So if you do not understand that, you should spend some time to understand that. So we should just put this exact solution to here, and remember that we have partial derivatives on t and x, and we should compute this derivative, and psi is function only of one variable. And that is why this prime, we use this prime notation, because actually psi is function only of one variable. So we compute this derivative with respect to this one variable of psi function, and then as the derivative of complex function, we should compute the time derivative for the argument x minus lambda t. So x and t are independent variables. That is why d over dt from this value is just minus lambda. And so we have minus lambda psi prime x minus lambda t. Is the time derivative of exact solution. Then we compute x derivative for the exact solution. Once again, psi prime x minus lambda t is the derivative with respect to just one argument of our psi function. And then d over dx for this complex x minus lambda t. And this is just unity, because dx over dx equals to unity. And that is why we can put this d exact over dt and d exact of the dx to our equation and see that indeed it equals to 0. That is why indeed this is the exact solution. I think that within the scope of our course, I will provide you with maybe a couple of practical problems, and one can be implementation of numerical scheme for the solution of this equation. And so if you implement numerically one or another numerical method, you can compare the simulated result with this exact solution. That is why it's so important for you to understand that. So you can choose different psi function. So you can use just like smooth function or step like function. And so usually the difficulties in numerical solution we have for discontinuous initial solution. And once again, so different properties of numerical methods can be demonstrated for different choice of initial psi function. Okay, so this is the linear advection equation, the exact solution, and the propagation of the signal in the positive direction of x-axis for the case of lambda greater than 0. A very important concept that you should understand is the characteristics. The concept of characteristics of the linear advection equation. So our exact solution looks like psi from x minus lambda t. So it means that the initial conditions propagate at a constant speed lambda to the right for lambda greater than 0 and to the left for lambda less than 0. So this is the simplest possible example of wave solution. So we have discussed it. The lines x minus lambda t equals to constant are called wave fronts. U of xt is called the signal or wave information, lambda is called the wave speed, and psi is called the wave shape or waveform. So that's not the all the equations. That's not the shock waves. It's just some abstract signal that propagates along x-axis. So the linear advection equation is equivalent to. So you can here you can see that if x minus lambda t equals to constant, then u is constant. And if x minus lambda t is constant, equivalent to dx over dt equals to lambda. So we can say that the linear advection equation is the same as u is constant for dx over dt equals to lambda. So the wavefronts dx over dt lambda are called characteristics, curves, or simply characteristics. So characteristics are curves, or here just straight lines along which the solution propagates without changing. So now, previously it was x and u, and this is the we plotted our graphs for this space, but now it's xt diagram, and this xt diagram is used for plots with characteristics. So suppose we have this. So you can imagine also that we have the third axis u, and so we can use it to plot our solution. Anyway, suppose that t equals to t1 equals to 0. So this corresponds to initial time instant. At this initial time instant, for example, here at this part we have non-trivial solution like our psi of x function. And then at t equals t2, our solution propagates to the right, and for t equals to 3 it propagates further. And we know that u should be constant for dx over dt equals to lambda. So for each point we plot this straight line dx over dt equals to lambda, and the solution propagates along this line. So it means that if we imagine our solution, here it will be at t equals to t2. It will be here, and we use this line. So these and these dots, they will all be on this blue line corresponding to characteristic line. So once again, characteristic is a line along which our solution propagates with no tangent. So the concept of characteristics is important from theoretical point of view. Is also important for construction of some numerical methods, especially from historical perspective. The whole classes of numerical methods were built using the concept of characteristics. Why is it so? Because once again, if we know the solution here at this segment, then we know the solution here because it propagates in the same manner along characteristics. If we solve numerically this equation, it means that if we need to compute the value on the next time step, you should just know the solution at some point at the previous time step. Usually you do not know the place where the characteristic intersects the previous time layer, but you can somehow interpolate or provide some way how to compute the value at the previous time step, and then propagate it along the characteristic to the next time step. So we will do it in one lecture. So the concept of characteristic is very important for the construction of numerical methods for hyperbolic equations. We did not name our equations as hyperbolic, but all that. So we consider only hyperbolic equations. We also will define I'll give you the strict mathematical definition of hyperbolic equation. Okay, maybe a couple minutes because we started later. Linear direction equation characteristics. Well, now the situation becomes more difficult. So, okay, for linear direction equation, maybe that's everything is very easy, and maybe even obviously that it's just signal that propagates with constant velocity. Now let's move to scalar conservation law, written in conservation form or quasi-linear form. Let's just define in the same manner the characteristic curve as dx of dt equals to lambda of u of x and t. So it's just the formal generalization of the same definition that was here. Here it was dx over dt equals to lambda, and lambda is constant. Then we say, okay, lambda is not a constant anymore. But anyway, let's define the characteristic in the same manner, like previously. Then if the solution is differentiable, then it remains constant along the characteristics. And it figure out that in this case, once again, the solution is constant along this characteristic line. Why is it so? We can compute the full derivative du over dt from this u. And once again, as derivative of complex function, we should compute the partial derivative du over dt, because we have t here, plus du over dt from x. But x is also a function of t. That is why it's du over dx and dx over dt. But dx over dt is lambda. And we get our equation, du over dt plus lambda du over dx. And it equals to 0, because it's the equation that we are going to solve. So it means that, therefore, in the case of solution of the Cauchy problem, is given by an implicit formula. So in contrast to linear advection equation, we have once again U is psi of x minus lambda u, but here lambda is not a constant. So here lambda also depends on u. And here we have a bit more complex object. So here we have implicit formula which defines the solution that propagates along our characteristic line. And indeed we can check that this solution, this is indeed the solution of our problem. How to do that? You can try to do it at home if you, so it's difficult for you to understand it so very quickly. You can just do this exercise and put this u to our equation. And for that you need to compute du over dt and du over dx. And once again, so psi is a function with respect to just one variable because it's our initial solution, depends only on x. So it's just prime notation for that. And then we should compute the derivative with respect to time from this complex. But here, once again, it's complex function. So dx over dt equals to 0 because x and t are independent variables. And you should compute the derivative of this product, lambda u multiplied by t. And so the derivative t over t is unity minus lambda u, and then compute this derivative from lambda u. And you can solve this equation, find du over dt, like this one. So what does it mean? Is it okay? Okay. And then in the same manner you can compute d over dx. Right? Since the value of u does not change along the characteristics, their slope also remains constant, and therefore the characteristics are straight lines. So the dx over dt equals to lambda of u is the characteristic, but along this characteristic the solution is constant. It means that for scalar conservation law, when your speed depends only on u, not x and t, then characteristics are again straight lines. So they were straight lines for linear advection equation, and they are also straight lines for scalar conservation law if speed of propagation depends only on u function. And interesting that, so actually this formula is the resulting formula, despite the implicit form, is suitable for computing the solution. So you can compute the solution using this formula. So this, in this case, it was not necessary to compute anything. Actually, we know that these initial profiles, so yes, some simple computations, right? But the initial profile propagates in the same form in the positive direction of x axis. Here you should compute. You should do some computations because here you and here you. But it is usually sufficient to use a simple iterative method substituting the value of u from the previous iteration into right-hand side. I mean that it's not very difficult to compute the exact solution from this formula using some numerical method like simple iteration. Okay, I think that may be enough for the first part of the lecture, and we can have a break. Actually, you can see that everything is not very difficult, but it needs some time to realize what does it mean, to understand. But actually all these concepts are very important because all the equations are very difficult. So it looks like, well, mass conservation law, momentum conservation law, and energy conservation law, everything is very simple. You can use some derivatives, and that's not true. And when you try to get good results for all the equations, you need to understand the structures of the solutions, and for that, it's better to start with this approach, with this simplified conservation law. That is why it's important for you if you would like to know how to solve hyperbolic models equations, to understand what does it mean. Okay, so for the scalar conservation law, the equation for characteristics is actually just the same. But now it depends on unknown solution. That is why the solution of the Cauchy problem is given by an implicit formula, like this one. And we checked that indeed if you put this solution to our equation, that it satisfies our equation. characteristics of the Hopf equation. So once again, this equation is called Hopf equation. So if we choose the flux function f of u as u squared over 2, we will get Hopf equation, so-called Hopf equation. The characteristic should be a straight line. So x equals to ut plus x 0. Why is it so? Because now we do not have just some abstract unknown lambda of u. So for Hopf equation, lambda of u equals to just u. That is why the equation for characteristic line is x equals to ut plus x0, where x0 defines the specific location at which our characteristic starts. And u is psi of x0. So we can see that the inclination of each of characteristic line is different. So in contrast to linear conservation, linear advection equation, where this u equals to lambda, and they are the same for all characteristic lines. So for linear advection equation, all characteristics have the same inclination angle. But for Hopf equation, for nonlinear case, each characteristic has its own inclination. If we assume that the solution is smooth, the characteristics cannot intersect. Otherwise, the solution at the point of intersection would be single valued. For linear advection equation, characteristics, they were not able to intersect, to cross, because they were all parallel straight lines. But here, we can expect some problems. Some problems because different characteristics have different inclination angles. So if we consider this characteristic line, then u equals to psi of x0, it equals to tangent of this angle alpha. If the function psi, where psi is the initial condition for our equation, increases monotonically, then this angle alpha also increases. So why is it so? Because u is psi of x0. So if psi increases, then this u increases, and then this alpha also increases. So this type of flow is called expansion wave. So when in some region we have this expanding, so the divergent characteristic lines. So an expansion wave is any region in which the wave speed u increases from left to right. So once again, we can choose different initial condition psi function. If we choose it in the form that it increases monotonically, then it means that in the region where this psi increases, so we have this divergent behavior of our characteristic lines. And that's okay, actually. In this case, they will not intersect. And for each characteristic line, we can use this equation to find the solution. So it means that in the area of expansion wave, we know the solution here, here, and here at the initial time instant. Wow. Oh, very convenient. I didn't know that I can do that. Okay, I should learn how to do that. Oh, yeah, great. I think it's possible to have several screens and, for example, switch between different books and drawings. Maybe it will be very useful. Ah, yeah, okay. I should learn how to use this dashboard. Okay, so in the expansion wave, we can find the solution along each characteristic line because we have just discussed how to do that. But we have some troubles if the function psi of x decreases monotonically. In this case, the intersection of characteristics is unavoidable. Why is it so? Because when psi decreases, then in this region, the inclination angles change in such a manner that sooner or later we will get the intersection of characteristics. So this region is called a compression wave. And the compression wave is any region in which the wave speed u decreases from left to right. The situation when the characteristics intersect correspond to the mechanism of the formation of shock waves for Euler equations. This situation is also called gradient catastrophe. But actually, we can find this t bar value and analyze in more detail this gradient catastrophe. A smooth solution to the problem ceases to exist at the moment in time t equals to t bar when at least two characteristics intersect. Why is it so? Because each characteristic corresponds to the initial solution, and then the solution propagates along this characteristic line. So one solution propagates along this line, another solution corresponding to this point propagates along another characteristic, and when we have intersection, we don't know which solution now is valid, because one came from here, another came from here. Here, we didn't have such problem because so they did not intersect. That's a problem. What should we do in this situation? Thus, even if the initial data are infinitely smooth, so you may hear this statement, and for hyperbolic models, for Euler equations, even if the initial data are infinitely smooth, during the evolution there may occur a moment when the derivative of the solution to the nonlinear conservation law becomes infinite at some point. It's called a gradient catastrophe. So a gradient catastrophe means we have intersection of characteristic lines. And as I told, we can find this moment, t bar. So it is this moment when the denominator in the expression for smooth solution of the problem becomes 0. So we did not discuss it, but even in code, if you have some division, you always should check that the denominator is not 0, because you can think that in your simulations it should be always greater than 0, but everything can happen, and you should always check that it's not 0. So here, if it is 0, it means that you have the intersection of characteristics. And if it is 0, you can find this t. You can find this t instant when it equals to 0. So this expression is for just arbitrarily scalar conservation law for any lambda of u. For Hopf equation, lambda of u equals to u, and characteristics can intersect only when psi function decreases. That is why psi prime of x less than 0. Then you can express t, so you can find the moment when denominator equals to 0 and choose the earliest possible time moment, because psi the psi prime of x is less than 0, it should be minimal value of these values. And so this is the earliest time instant when you will have the intersection of characteristics. How will it look like for in your numerical solution, or is just the illustration for exact solution? So suppose we have this psi function, and it has two parts, so increasing part and decreasing part. And as we have discussed, so for the part where the psi function increases monotonically, then you have the divergent behavior of your characteristic lines, and they will not intersect. So the extra is the abscissa of extreme point. But here, in the region where psi decreases monotonically, you will have the intersection of characteristics. And here, all the characteristic lines are parallel to each other, like for just linear advection equation. It means that for some t1 value that is not too big, your profile will change in such a manner. Here you will have some stretching of a profile, or it's like a expansion wave, and here you can get the sharpening of your front. So this is the behavior of the formation of a shock wave. So at t2 that is greater than t1, you will get more stretching and more sharpening, and at some instant, so the function tries to be not a function. So it is not valid picture, because to 1x you're not able to have different values of your function u, right? So it means that theory says that something should change at the moment when characteristics intersect. And from theoretical consideration, you should have now the shock wave. So when your characteristics intersect, your solution becomes shock wave. So shock wave is like a black hole when different characteristic lines they converge, and on the shock wave they converge, and the solution just forget information that propagate at all that characteristics, and from that point it propagates along some other trajectory. So yes, I like this. So I use different. Once again, it's not my ideas and so on. It's just common knowledge, and I use very good books, and I try to find good parts that can illustrate all these concepts. So this is from Lenny book, Computational Gas Dynamics. So a conflict occurs when two wavefronts with different signals meet. Such conflicts can be resolved by jump discontinuity or shockwave jump discontinuity. So you should know the synonyms in the solution known as a shockwave. Shockwaves are different from other waves. So shockwaves are governed by jump relations and the theory of weak solutions. So our next slides will be about jump relations and weak solutions. So shockwaves are the black hole of waves. They absorb any waves that meet, effectively destroying them, and then the signals they carry. Notice that shock can occur anytime wavefronts converge, despite the fact that the boundary and the initial conditions may be completely smooth and continuous. So you may think that, so you'll set something very, very smooth. Anyway, you can get the shock wave because it's just the property and the nature of your equations. In contrast, for example, for parabolic equations. So maybe and your physical intuition says that, well, I know how to solve heat transfer equation or diffusive equation. We don't have these effects in parabolic equations, right? So if you will solve, for example, heat transfer equation for this initial profile, you will get some propagating of this heat. So the behavior of gas dynamics equations, of Euler equations, of hyperbolic models, they're totally different. That is why I said to you that so nowadays it's difficult to find an expert in all types of flows, equations, so on, because the properties are very, very different. Okay. Yeah. And this is the example of how the different characteristics they converge, and this is a black hole of waves that absorb any waves that they meet. This is just to relax. Actually, I have some paper. I have research in which we got in explicit manner the mechanism of formation of shockwave. One of my field of interest, as I told to you at the first lecture, is the numerical simulation of propagation of detonation waves, so supersonic combustion waves. And this can be done also close to reality, solving 2D or 3D equations with real chemistry and so on. But also some theoretical considerations are important. I tried to explain to you at the first part of our lecture that analog equations, simplified models are important. So even Euler equations, although they're very difficult, you can try to solve them in 1D. And also we solve them not only in 1D, but also in shock-attached frame. So to study the dynamics of propagation of wave in complex media, we moved to shock wave to reference frame attached to a shock wave. It's a non-inertial reference frame. And this is example of the problem of propagation of a shock wave in a media with varying density, because in reality, for real technical devices such as detonation engines and so on, the propagation, the distribution of parameters is not uniform, and in this case, the mechanisms of propagation of waves in such a media becomes much more complex in comparison with just uniform media, and so. This is to check our algorithm, we considered this known test case. Shu is one of the most famous in the world. So he developed the ENO schemes, so he is very famous for that. And then the Journal of Computational Physics is the main journal in the world where people publish their novel results on the development of numerical methods. So in this journal, each paper should contain, at least to some extent, something new in the development of numerical methods. And they consider this test of propagation of shock wave in a media of variable density. And in this case, the shock wave propagates, and when it propagates when it meets the region of increasing density, it likes something prevents you from propagation. And that is why you have the signals that propagate in form of convergent and divergent characteristics, like very simple, very similar to this picture. So this is so that is why these analog equations are important. So this is just abstract equation and just abstract initial condition that does not correspond to any real life. But here it corresponds to real life because you can consider the real shock wave with the realistic Mach number. We discussed what does it mean Mach number and realistic wavelength of this disturbance, and you can see the convergent and divergent characteristics. How does it look like for density, velocity, and pressure? So you can see it's some this oscillation behavior, but this front becomes steeper and steeper. So you can for example see here. You can see it becomes more sharp, sharp, and sharp. And actually, this is the mechanism of formation of a shock wave in real gas dynamic simulation. How they becomes sharp. And the mechanism is just the same as we just discussed for scalar conservation law, right? We will also consider this paper one more time when we will discuss numerical methods, because this is a very good test case showing that actually we need to use high order methods. Actually, this is example for example, these dots correspond to, I don't know, but it's either low accuracy order method. So the real solution includes this oscillation. So it's not the numerical oscillation. This is a real response of your flow behind the shock wave to these disturbances in density. And the problem is that you use not high enough accurate numerical method. You will just lose all these amplitudes, pulsations, and that's it. But at the same time, if you use, for example, second order method, you will get much better result. Third order method, also better result. But for the fourth, fifth, and so on order methods, you will see that actually the result will be just the same. So in reality, in gas dynamics, so all these mechanisms also exist, and so I try to show you that. Weak solution. So okay, we described this situation when the characteristic lines they meet and converge, and we have a shock wave. But in this case, we get some discontinuous solution, and the problem is that we are not able actually use our differential equations because we have some discontinuity. It's not possible actually to differentiate across the shock wave, and that was a big discussion in community in 50s or maybe 60s, and maybe nowadays some people still do not admit that. Maybe in what does it mean, shock capture numerical methods. So nowadays the majority of numerical methods are shock capture, and it means that we compute the flow field, and we do not think about if you have discontinuous solutions or continuous solution. Numerical methods computed anyway. But from theory numerical, so from theoretical point of view, it means that theoretically we have a shock wave that is infinitely thin discontinuity. But our numerical method just, in one sense or another sense, just take a derivative across this discontinuous solution. And that's a bit confusing, and people thought so they thought that it's incorrect. And they tried to track all the shock waves in simulations. And if you have one or two shocks, it's possible. But then you have hundreds of shock waves, or you have 2D problem with very complex flow structure. It's not possible to track your shock waves. Anyway, from theoretical point of view, we should introduce the concept of weak solutions. So again, consider the Hopf equation, and here, Green-Gauss formula. So at the previous lecture, we established the relationship between integral form of notation for Euler equation and differential. Actually, I did not say that, but we used Green-Gauss formula. So it's known from mathematical analysis that, for example, consider this equation, and D is an arbitrary area with boundary gamma, and this is Green-Gauss formula. So we can integrate our equation over the arbitrary area and express it through the integral over the boundary of this area. So the weak solution of this equation, for example, Hopf equation, or more general scalar conservation law, when f of u is some function not u squared over 2, is any piecewise differentiable function that satisfies to the following condition for any choice of contour gamma in the semi-plane t equals to greater than 0. So it means that weak solution of this equation is the solution that satisfies not the differential but in integral form. That's it. So it means that integral form of equations, it actually contains weak solutions, and weak solutions are just solutions of this integral form of our. So they are actually the same, but not the same, because the difference is in the existence of discontinuous solution for this notation. And that is why, if we want to describe the behavior of this shock wave or discontinuous solution, we should work with this equation, not with this one, because formally it does not contain discontinuous solutions, but with this one. How can we do that? We will repeat it when we will discuss the Euler equations, but now we can derive the jump conditions for just Hopf equation. So today's lecture is like a sample of the rest part of our course, because it's a bit difficult because I introduced many concepts, and later we will analyze in more detail each of them from both theoretical point of view, numerical point of view. But now I just introduce many concepts. So we discussed the mechanism of the formation of shock wave, and now we should derive the relationships that describe this shock wave. So we know that if the characteristics line intersect, they should intersect in the form of a shock wave. It is known that shock wave is a discontinuity, and the parameters in front of the shock wave and behind of the shock wave, they could not be just arbitrarily. There should be some relationship between them and in connection with the speed of propagation of this shock wave. Let's get these jump conditions. They also called Rankine-Hugoniot conditions. So Rankine is an American scientist, and Hugoniot is French scientist, and they obtained, I don't know, maybe independently, but I also have, when we will discuss it for gas dynamics, I have some slide with historical perspective of this thing. But that's not very obvious. So just 100 years ago, people do not understand all these things, and they did not understand how is it possible to have discontinuous solution, and they did not know how the parameters should change across this shock wave, what will happen with energy, density, entropy, and even very famous scientists, they made mistakes because they believed in actually wrong things. So consider the shock wave that propagates, and the U sub 0 is the parameters in front of the shock wave, and U1 parameters behind the shock wave. So d is the velocity of propagation. That is why it's so. So consider this plane xt, and p prime is the trajectory of our discontinuity. So let's choose this contour a prime, b prime, b, in such a manner that these points a prime, b, p prime, b on the opposite sides of this discontinuity. So t1 and t2 just arbitrarily two time instants. So 0 means the parameters here, so they have the parameters 0. Actually, this is just u sub 0. So in gas dynamics, it will be rho, u, and p sub 0. And here, parameters behind the shock wave. So the goal is how to find the parameters. So in gas dynamics, the goal is how to find parameters behind the shock wave, if we know the speed d. But actually, here is how to find this velocity d. And as we discussed, we should work with this integral form of our Hopf equation, because we want to find weak solution. So here is the integral over some contour gamma. Let's specify this general form of notation and use this for this gamma a prime, b prime, b. Okay, so this contour corresponds to this gamma in this equation, and we just rewrite it. So this integral equals to four integrals for the part a prime, b prime, and so on and so on. Maybe some sign is wrong as far as I remember. Or maybe not. Yeah, it looks like here it should be b a, right? A prime, B prime, B, and so these limits of integral are, wrong, mixed up. I should, because so this slide was prepared a couple of years ago. And then we carry out the following procedure. We move A to A prime close to each other, so trying to decrease this segment to 0. But anyway, A should be on one side of this trajectory of discontinuity, and A prime should be to another side of our discontinuity. And in such a manner, this integral goes to 0 because the length of the segment A prime and B prime B goes to 0, and we have only integrals for these two paths. And then we take into account that dx equals to d dt, and integral. So we now use only one variable for integration, t, and that is why the limits for our integral are from t1 to t2, where t1 and t2 just arbitrarily functions. Yeah, and here also wrong. And then we collect them into one integral. Anyway, so we collect them into one integral, and then because of these t1 and t2 time instant are just arbitrary time instants, it means that this integrate function should equals to 0. And then we get the relationship between u sub 0, u sub 1, and d. So the parameters in front of the shock wave, behind of the shock wave, and the speed of the shock wave should not be just arbitrarily. So there should be some relationship between them. In the same manner, so we have such situation in gas also. So if you have density, velocity, and pressure in front of the shock wave, and some intensity of the shock wave, for example, after explosion or something like that, we can compute the parameters behind the shock wave. So they can be computed. We can find the d from this equation. D equals to 1/2 from u0 plus u1. So actually, it's just an average value between these values, u sub 0 and u1. But once again, that's only everything for just one scalar Hopf equation. In literature, highly likely you will find some slightly different notation, general notation. So if you solve the equation just scalar conservation law, but with, Hopf equation with f from u equals to u squared over 2, then this is jump condition. But at this stage, it can be interpreted in the following I mean general notation, that we don't want to use the Hopf equation, but we want to keep this general flux function. So if you want to keep just general flux function, it should be here, f and f. And then we carry out just the same procedure, but we do not specify that flux function equals to u squared over 2. And we get this one and this. And so in the majority of books, the Rankine-Hugoniot jump conditions are written in the following form. Or not 0 and 1, so the parameters with 0 are right one, and with 1 left one. And this is the relationship that between parameters to the left and to the right of the discontinuity that propagates with the velocity d. So if we substitute f like bolt and straight flux vector for Euler equations, and it will be also conservative variables vector. So just in the same view, it's valid for Euler equations as well. So actually, these Rankine-Hugoniot jump conditions are also valid for Euler equations. That is why I also presented this formula, because we will meet it several times later. There are, however, some mathematical, not difficulties, but issues. So, the same equation, when written in non-conservative form, may correspond to several conservation laws. So, what does it mean? So, consider this Hopf equation, right? And we carried out the following thing. So, this Hopf equation corresponds, so it's quasi-linear form of notation, non-conservative form. It corresponds to this conservation equation, because thus we can just differentiate and get from this one, or quite contrary, we can put this u to the brackets and to the d over dx sign to differentiation. Then we discussed that there is a weak solution, and we analyze these weak solutions and get that the velocity of the shock wave in this model is u sub 0 plus u1 over 2. But we can just multiply both sides of this equation the same function u. For example, from a mathematical point of view, this one and this one, they are just the same, because we just multiplied both sides of this equation to the same function u, right? They are the same. But if we will carry out all the same manipulations, we will get another definition for weak solution, and this another definition for weak solution will provide us with another speed of the shock wave. And that's bad, because actually, the reality is the unique, and it's not possible to. That's bad if we get different results, for example, for the speed of propagation of a shock wave, depending on some mathematical manipulations. So the problem is, and the thing is, that we should work with physically relevant initial equations, and physically relevant equations follows from physics. So we started with Euler equations, and we should work with these Euler equations. We should not multiply them to densities, velocities, and so on. So we should start with relevant equations, and on this way we should get correct definitions of weak solutions, shock waves, and so on. It's not about different mathematical manipulations or something like that. So the problem is that this integral law is correct. It follows the nature, or physicists. There is some agreement that indeed we should solve these equations, and many phenomena in reality, they correspond to this equation. And this is a wrong conservation law. You can write them, but the reality does not correspond to this model. That's it. So something similar. Okay, we will talk it about later. So very important. Keep in mind that although this is very mathematical, all this stuff, but we work with some physical problems with nature. That is why we should keep it in mind. Okay, I think the last topic, the Riemann problem for the Hopf equation. So as I told, it's a sample of our course. So the idea of our course, as I told to the first lecture, is the following. So I will try to explain you the basics of finite volume methods as the most powerful methods and widely used nowadays for computational gas dynamics. And the finite volume methods, they rely on some numerical flux function. And numerical flux function is one or another approximation of exact method of computing of the numerical flux, Gordon flux. And so the computation of numerical fluxes in finite volume methods depend on the solution of Riemann problem for gas dynamics. And the solution of Riemann problem depends on the knowledge of relationships for shock waves and rarefaction waves. I will try to follow and to explain you all these logics later. But from theoretical point of view, we should know how to solve so-called Riemann problem for hyperbolic problems. What is the Riemann problem? Riemann problem is a piecewise constant Cauchy problem for the hyperbolic problem. So if you have one equation, scalar conservation law, or system of equations of hyperbolic type, so we can solve the initial value problem with discontinuity in the initial data. So suppose that the x equals to 0, for example. So if x less than 0, we have u left some value, and for x greater than 0, we have u right. For example, 1 and 0. So this is the Riemann problem. So this constant 1 and 0 can be different. And the question is what the solution will be. For Euler equations, for scalar conservation laws. So suppose this problem. So if x is less than 0, we have 1. If x is greater than 0, we have 0. Let's try to construct the solution for this Riemann problem. So in xt diagram, so this is u equals to 0, u equals to 1, as I have shown just you. We know that the solution has the form of, can be defined using characteristic lines, and the solution propagates along these characteristic lines. So let's plot characteristics in this case. Characteristics are x equals to ut plus x0, right? We have discussed it here. This one. So these are characteristics, straight line characteristics for Hopf equation. So we solve the same equation, and we now want to plot these characteristics. Okay. So here u equals to 0. That is why it's just straight vertical lines. The solution does not change because the inclination line, so they're vertical. But here u equals to unity. That is why we have some inclination of these green characteristics. We have intersections. So we discussed that this conflict should be resolved using shock wave. So the solution should look like this one. So characteristics meet here, and they converge to a shock wave that works like a black hole. And we just derived that the speed of a shock wave should be u here to the left, to the right, to the left, divided by 2. So dx over dt should be 0.5, right? And that's it. So the solution of the Riemann problem for Hopf equation for this initial data is 1 for x over t less than 1/2, and 0 for x over 2 greater than 1/2. So if we plotted this function, it will be just discontinuity that will propagate to the right with the velocity 1/2, like for linear advection equation, right? So it's a shock wave with here 1, 0, and it will propagate with the velocity 0.5. The problem occurs when we just change these parameters 0 and 1. So let us consider the Riemann problem when for x less than 0 we have 0, and for x greater than 0 we have 1. If we will try to do the following, just the same consideration, we will meet some problems. Actually, now the characteristics to the left are vertical, right? And characteristics to the right are, inclined to some angle. And the problem is that we do not know what to do here in this region. We can propose the following solution. Suppose that maybe, like in previous case, there is a shock wave, but in contrast to previous case when the characteristics they converged on the shock wave, now the shock wave emits these characteristics, and this is one of the proposed solution. But it happened, so the reality is that this is wrong solution. So the shock wave, it cannot emit characteristics, and the correct solution is the following. So here we have the same characteristics, but in this region, there is a so-called simple centered expansion fund. So here you can check that if you take in this region solution the form x over t, it will really satisfy the Hopf equation. And the solution will have like this one. So constant, and here is the linear solution. So for Hopf equation, the expansion wave has a form of just linear function. Why is it so? Why this solution is wrong? This solution is wrong. This solution is wrong because we did not take into account the entropy inequality. So like in all equations, we have mass, momentum, and energy equation. But I also told that we should take into account second law of thermodynamics. Here, we did not take into account. Here, we just analyze our conservation law. That's it. But if you take into account the second law of thermodynamics, it's called Lux entropy condition. The jump condition, shock wave must satisfy the following condition. So this is speed propagation to the left. It should be greater than speed of shock wave, and it should be greater than wave propagation to the right of the shock wave. Or it can be proved that it's just the same, that wave or characteristics terminate on shocks. Waves or characteristics never originate in shocks. So we can formulate this criteria in different words. So it means that this situation when they originate on the shock wave characteristics is forbidden. It's wrong. It does not fulfill to the second law of thermodynamics. And this entropy condition is associated with the name of Lux. So I think the last slide for today, Peter Lux is one of the most famous mathematicians of the 20th century. He just died, so this year, at the age of 99. It's the American mathematician, Hungarian born. And so known for Lux equivalence theorem. So there's a big list of his results. But maybe one of the most known Lux equivalence theorem, we will discuss it next lecture. He contributed to pure mathematics, he contributed to numerical mathematics, he is founding father for just numerical methods and the whole approaches that are used worldwide today. He also took part in American atomic project and so on. So a lot of things in our course is associated with his name. Specifically, this entropy condition that says that this solution is wrong and this solution is correct. And all this is just for one very simple actually model. So for sure, linear direction equation is much more simpler, but actually this is just one difficulty. We just consider this u velocity. And even in this case, we got expansion waves and the shock waves and mechanism of shock formation and so on and so forth. So okay, I think that's all for today. So it was, I think, very important, but maybe not very easy lecture. But from the next lecture, we will start with numerical methods. So now we understand the general, picture of the solutions that we would like to compute. Now we should know how to compute that. So okay, we must be able to compute these shock waves. And for the shock waves, it is known that I tried to explain to you that this differentiation across the shock leads to to spurious oscillations, and so how to deal with that and so on. Okay, so thank you.